Hello, my dear students. So today we're starting with the design of numerical based upon the design of centrifugal pump. Okay, so let us start. Okay. So now see, this is the design. This is the project that we need to design it. Design a centrifugal pump for the following specification: total static head 50 meters. Okay, total static head 50 meters. Then discharge 100 meter cube per hour. Okay, and the medium is water over here. Okay, so now what can be what is the variation, what kind of variation made possible over there? So instead of 50 meters there may be a 10 meters. It means that it head maybe a 10 meters, maybe 20 meters. Now here the total static head is given. So in some numericals it may be separately the static head 2 meters plus delivery head may be a 8 meters. Likewise the split up also given. Okay, so according to the given thing, start with the design. Now next one, discharge is 100 meter cube per hour. Generally, this discharge is given in terms of LPM also, that is liters per minute, LPM or liters per hour. Okay, so finally we have to convert this discharge in terms of meter cube per hour. And which things we are going to design? We design a suitable motor, design impeller. Okay, then design impeller, shaft, bearing, and the housing. Okay, so now we start with the actual thing. Okay, now discharge is given, that is 100 meter cube per hour. Okay. So first initially I have to convert it in terms of meter cube per second. So divide by 3600, you will get the answer at 0.02778 meter cube per second. Sometimes if the discharge is given in terms of LPM, then total LPM divided by 60 into 1000, you will get the answer in terms of meter cube per second. Now here the total static head given Hs is equal to 50 meters. So now as per the standard references like Modi set and other books are there. So with reference to that, according to this references and some pump manuals, so generally 10% of the total static load can be considered as a static suction head. Okay, so total static head Hs is equal to static suction head plus static delivery head. Okay, so now here I have assumed the value of Hs as 10% of the total static head, that comes out to be 5 meters. So the remaining is a 45 meters. Okay, so I have assumed out of 50, 5 meter is a total static suction head and 45 meters as a static delivery head. Okay, now which are the things we have to find it out? We have to find out the value of Hm, that is a manometric head. So for that reason, I have to find out the losses in a suction pipe, losses in the delivery pipe, then the velocity losses in the suction and the delivery pipe, frictional head loss, again the head loss in the impeller. So all these things that we have to calculate it. So for that reason, we have to make certain assumptions. So first of all, assumptions regarding the suction and delivery pipes. Okay, length of the suction and delivery pipe. So generally 40% greater than the static head, we can assume the length of the suction pipe, otherwise given. If given, then select, then assume those values, otherwise make 40% greater than the static head. So 1.4 into 5, so 7 meters, that is the length of suction side, as well as the length of the delivery pipe. I have assumed 1.4 into HD, which is equal to 1.4 into 45, that comes out to be 63 meters. Okay, now determination of pipe diameters. So now we know the formula. Q is equal to area of the suction pipe into the velocity in the suction pipe. Q is equal to AS into VS. So AS is the area of the suction pipe and VS is the velocity of the liquid in the suction pipe. Okay, now as per the standard references, velocity in the suction pipe should be lesser than 3.5 meters per second in order to avoid the cavitation. Okay, so for the safe side, I have assumed the velocity Vs is equal to 3 meters per second. Okay, so Q is equal to 0.02778 meter cube per second and V is equal to 3 meters per second. So with reference to that, we are getting the diameter ds as comes out to be 0.1085 meters. That is nothing but 108.5 mm. Now we have to standardize the pipe. Now the standard pipes are available in the form of inches. Okay, so diameter of ds. So that's why I have divided by a 1 inch. 1 inch is equal to 25.4 mm. Then our answer is comes out to be 4.27 inches. It means that I have to select the standard pipe which is greater than 4.27 inches. So standard pipe is available as 4.5 inches. Okay. Hence, I have selected the standard suction pipe diameter as 4.5 inch, that is 114.3 mm. Similarly, now I have assumed the standard suction pipe as 114.3 mm. Okay. Now here answer comes out to be 108, but this is not a standard diameter of the pipe. So standard diameter of the pipe is 4.5 inch, that is 114.3 mm. So I have to recalculate the velocity of the suction pipe by considering this as a diameter, and this comes out to be 2.7073 meters per second, which is again less than 3.5 meters per second. Hence we can say that our design is safe. Next, determination of a delivery pipe. Now, in order to consider the hydraulic losses in impeller, delivery pipe, and in order to consider the hydraulic losses in the impeller and the delivery pipe, the diameter of the delivery pipe has to be kept somewhat smaller. It means that there is a velocity losses. Okay, so in order to consider that losses in the pressure, we have to consider the smaller pipe diameter somewhat smaller than the suction pipe diameter. So we have considered the diameter of the suction pipe is 4.5 inch, so somewhat smaller. I have considered here diameter of delivery pipe as 4 inches, that is nothing but 101.6 mm. So now from this, Q is equal to area of the delivery pipe into the velocity of the liquid in the delivery pipe. So that is comes out to be 3.4265 meters per second, which is less than 4 meters per second. Hence we can say that our design is safe. Next, determination of manometric head. We know that HM is equal to HMS plus HMD. It means that net manometric head is equal to manometric suction head plus manometric delivery head. Now, first of all, we have to calculate manometric suction head. So, which are the things we have to consider? So, manometric suction head is nothing but the static suction head plus velocity head loss in the suction pipe plus loss due to the friction in the suction pipe plus head loss due to the strainer plus head loss due to the number of bends. So, static suction head we are considering as a 5 mm, already we have assumed. Velocity head loss Vs squared upon 2g. Okay, so that is comes out to be 0.3736 meters. Vs already we are calculating it in the previous page. Loss in the suction pipe HFS is equal to 4FLV squared upon 2G. This is standard formula. Now in this case we have considered F. F is the friction factor, that is equal to 0.001 to 0.003 for the new smooth pipe and 0.004 to 0.008 for old rough pipe. But for the safer side, we are assuming friction factor at 0.008. Okay, LS is the length of the suction pipe, already we have assumed as a 7 meters. VS already we have calculated as a 2.7073 meters per second for the pipe diameter of 4.5 inch, and diameter of DS is equal to 4.5 inch, nothing but 0.1143 meters. Now if you put all this, we are getting the value of frictional loss in the suction pipe. HFS is equal to 0.0732 meters. So now head loss of the strainer, I have assumed it to be 0.2 meters. Now here total head is 50 meters, so I can assume 0.2 meters. But now if your total head required is 10 meters, so accordingly you can assume the lesser value. You can assume 0.02 meters also or 0.01 meters also. Okay, so that is again depending upon the total head. No, next one, head loss due to the bends, where n are the number of bends into the loss due to the each bend. So here I have assumed the loss due to the each bend as 0.1 meters. So 2 into 0.1. So losses due to the bends comes out to be 0.2 meters. Now again this loss due to the bends you can assume lesser, that is 0.05 or 0.02 meters also. Now HM for suction side I have calculated as 5 plus 0.3735 plus 0.7321 plus 0.2 plus 0.2. So that comes out to be 6.5056 meters. Now we have to check it for that much amount of manometric suction head whether the cavitation occurs or not. So for that reason, as far as the practical procedure is concerned, the pressure available at the eye of the impeller is equal to H atmosphere minus vapor pressure of the liquid minus pressure head at the manometric pressure head at suction side. So H atmosphere is equal to 10.3 for water. You can get this value from the pressure from the enthalpy charts. HV is the vapor pressure for the water, that is 2.3 meters at 30 degrees centigrade. and HM for suction side we are getting it at 6.5056 meters. So finally my answer is comes out to be pressure available at the eye of the impeller comes out to be 1.4944 meters, which is less than the vapor pressure, that is nothing but 2.3 meters. Hence the cavitation occurs. It means that initially whatever we have made the assumptions, that is wrong, because here the pressure available at the eye of the impeller falls below the vapor pressure of the liquid, that is 2.3 meters, and hence we need to reduce the suction head so that the pressure available at the eye of the impeller is greater than the vapor pressure. Okay, so here I have made the correction as now initially I have assumed the HS as 3 meters. So right now I have assumed the value of HS is equal to 3 meters. Instead of 5 meters I have assumed it to be 3 meters, so that the delivery head as a 47 meters. Okay, so now for this 3-meter head I assume the value of length of suction pipe as 5 meters. Okay, so the velocity head loss is equal to Vs squared upon 2gt, same 0.3736, which remains same. Only the change is that the HFS, this HFS value will be changing. Okay, that is 4 FLV squared upon 2gt. Okay, and that value is comes out to be 0.5229 meters because length has to be changed. The assumptions regarding the losses in the strainer and losses in the bends will be as it is, that is 0.2 meters. So now HM for suction side is comes out to be 3, that is we are changing it, right? 3 plus 0.3735 plus 0.5229 plus 0.2 plus 0.2, that comes out to be 4.2964 meters. Now the pressure available at the eye of the impeller, it comes out to be 4.294 meters, which is greater than 2.3 meters, and hence we can say that now for that much amount of HS as 3 meters, cavitation won't be occurs. So for all further calculations we have to make HS is equal to 3 meters and HD is equal to 47 meters. Now HM for delivery side, that is nothing but the manometric head for the delivery side, that is nothing but the summation of static delivery head plus the velocity head loss plus loss due to the friction in the delivery pipe. Instead of suction pipe you have to write down the delivery pipe, then the head loss due to the delivery wall plus head loss due to the number of bends in the delivery side. So HT is equal to 47 meters. Velocity head loss is equal to VD squared upon 2G, that comes out to be 0.5984 meters. Again, losses in delivery pipe, HFT is equal to 4FLVD squared upon 2GD. Okay. Again, F I have assumed the friction factor at 0.08 as discussed in the suction side. Length of the delivery pipe 65.8 meters. Velocity of the liquid in delivery pipe 3.4265 meters per second. Diameter of the delivery pipe 101.6 meters, it is 0.1016 meters. Okay, so from this I will get the value of frictional loss head in the delivery side as 12.4017 meters. Okay, now head loss due to the delivery wall assume 0.2 meters, and number of bends I have considered in the delivery side as a 4. Okay, and the head loss due to each bend is 0.1 meters, so the total head is 0.4 meters. Now the HM for delivery side is equal to 47 plus HFD, that is 0.5984, okay, plus this 12.4017 plus 0.2 plus 0.4. So finally that is comes out to be 60.60 meters. Now if I add HM for suction side and HM for delivery side, the answer comes out to be about 64.89 meters. That is I have roughly considered as 65 meters for simplicity. Now next, motor selection. Power P is equal to rho GQ into HM divided by overall efficiency. What is the value of rho for water? 1000 kg per meter cube. G 9.81 meter per second square. Q is equal to 0.02778 meter cube per second, and HM is equal to 65 meters. And overall efficiency is nothing but the effect of manometric head, volumetric efficiency, mechanical efficiency, and the manometric efficiency. So I have assumed the value of these values of all these efficiencies such that the overall efficiency should not fall below the 70%. So with these references or with these assumptions, I have got the overall efficiency at 72%. Okay, so from this I will get the value of power required as 24.382 kilowatts. Now we have to select the RPM of the motor, and RPM of the motor selection will be based upon this specific speed of the pump. Now see, Ns is equal to the n into square root of q upon hm to the power of 3 by 4. This is the formula if you have to put the value of q in terms of meter cube per second. In terms of meter cube per second. Now Ns, as per as the standard pump manuals, so Ns should be kept in between 15 to 40. Okay, for centrifugal pump. So instead of playing with those numbers directly, I have taken the standards RPM of the standard motors, that is 960 rpm, 1440 rpm and 2880 rpm. So I know the value of hm is equal to 65 meters. Okay, and ns I have to find it out. So now what I have to do, I have to put here value of hm 65 meters, value of q 0.02. Already we are calculating it at the initial level, and now only we have to vary the value of n, and we have to calculate the value of ns. Now put the value of n as 960, so corresponding value of ns comes out to be 6.982. For rpm n is equal to 1440, ns comes out to be 10.47, and for the rpm of 2880, ns comes out to be 20.94. So now out of these three values, ns is equal to 20.94, which is in the range of 15 to 45, 15 to 40, and that's why we have to go for the standard rpm as 2880 rpm. Hence, we have to selecting the standard three-phase AC motor with 25 kilowatt at a rated speed of 2880 rpm. Now this is 25 kilowatt. The standard value comes from PSG 5.125. Okay. Now impeller design. Now material generally on impeller we have to go for the cast iron. Now since the water is not dusty water, but turbid water, it's a clear water, and hence I have to go for open impeller as shown over here. Okay, not open impeller, I have to go for the closed impeller. If it's a turbid water, I have to go for the open impeller, but right now it's a clear water, since I have to go for a closed impeller. Now during the closed impeller there will be a shroud plate as well as there will be a cover plate also. So both plates also there, and the number of backward code wins are there. So now we have to design the dimensions. Which are dimensions of the design? That is the diameter of the impeller at the impeller eye, then the diameter of the impeller at the exit, means maximum diameter of the impeller, then the width of the impeller at the inlet, width of the impeller at the exit, that is BO, then diameter of the shaft that we need to assume, that we need to decide it. Now first of all, on what basis we have to start with the design of impeller. Okay, now this is the velocity triangle for the impeller, that is u1 absolute velocity, v1. This is the velocity triangle at the inlet, and this is the velocity triangle at the exit. That we'll see it one by one. So first of all, u2 is equal to square root of u2 is equal to ku into square root of 2g into hm. Now ku, range of the ku is given as 0.95 to 1.25 with the standard references. Now our value is comes out to our value of the specific speed is as 20 point something, and the range is between 15 to 40, and that's why I have to consider the nearer value to 0.95. So I have assumed the value of ku is equal to 1.05, hm 65 meters. Okay, so from this I have got the value of u2 as 37.4969 meters. Okay, now from this value of u2 is equal to pi into d2 into n divided by 60, then diameter comes out to be 0.2486 meters. So I have considered somewhat higher value, that is nothing but 0.26 meters. This is the outside diameter of the impeller. Now inside diameter of the impeller, again certain assumptions were to made. So diameter d1, that is inside diameter of the impeller, can be taken as one third, that is 0.33 to 0.5 times of the outer diameter. Okay, for simplicity I have considered just half of it, that is 0.5 times diameter d2, so that comes out to be 0.13 meters. Okay, from this I have calculated the value of u1, again pi into d1 into n1, pi into d1 into n divided by 60, and that comes out to be 18.7485 meters. Now these assumptions were to made it, but now with those assumptions, whether the total head generated or imparted by the impeller, whether it will be greater than the manometric head or not, I have to check it. Now what is the value of u2? 37.49. What is the value of u1? That is 18.7485. Now see, this is a standard formula. So from this we look at we are notice that u2 squared minus u1 squared upon 2g is equal to 53.74 meters, which is less than the value of hm is equal to 65 meters. It means that with these assumptions, we won't get the total amount of head. Okay, so that's why we have to increase the value of d2 and increase the value of d1, so that the total head developed will be greater than the manometric head. So now instead of 0.26 meter, I have considered d2 is equal to 0.28 meters, means 280 mm, and the corresponding value of u2 is equal to 42.22 meters per second. Now just half of this d2 is d1, that is 140 mm. So u1 is equal to 21.11 meters per second. Now if you put all those two values in this formula, and if you check it, then you are getting it as the head developed by the pump is 68.1394 meters, which is greater than the manometric head. So now whatever the assumptions we have to made over here, now those are, we can say that those assumptions are correct. Okay, we move ahead. Now next one, determination of velocity components by using the velocity triangle are the inlet vane angle theta 1 is equal to v1. If you consider this inlet vane angle theta 1 is equal to, that I have to find it out. So tan of theta 1 is equal to v1 upon u1. Okay, now v1 is equal to velocity of the liquid in the suction pipe, that is equal to 2.7072 meters per second, and u1 already we have made the assumptions in the previous page, that is 21.11 meters per second. So finally I'll get the value of theta 1 is equal to 7.307 degrees. Now work velocity at the exit of the impeller means VW, that have to find it out. So for that reason, this is a standard formula for manometric efficiency. So manometric efficiency is equal to G into HM upon VW to U2. Now manometric efficiency already we have assumed 0.85 and HM 65 meters. So and value of U2 is equal to 42.22 meters per second. Now from all this we will get the value of VW2 as 17.7682 meters per second. Now determination of velocity components as shown in the velocity triangle by using the flow velocity at the exit of the impeller. Flow velocity means what? VF2. If VF2 value के लिए so VF2 flow velocity is equal to psi into square root of 2g into hm, and psi can be taken as in the range of 0.1 to 0.25. So for simplicity, I have assumed the value of psi is equal to 0.15 hm 65 meters. So from this, I will get the value of Vf2 is equal to 5.3562 meters per second. Similarly, vane angle at the exit, that is nothing but the theta 2 vane angle at the exit. Okay, theta tan of theta 2. So if you go for tan of theta 2, that is nothing but जहाँ इतना सा angle है ना, angle 5 to find it out, that is nothing but Vf2, the value of Vf2 upon Vf2 upon, it will be u2, total value u2 minus vw2, meaning this length, if you refer this velocity triangle. Okay, so now u2 is equal to 42.22 meters per second and vw2 is equal to 17.7682 meters per second. Okay, and vf2, that is 5.3567 meters per second. Okay, so if you put all this, I will get the value of vane angle at the exit theta 2 is equal to 12.35 degrees. Similarly, blade angle, there is a value of alpha 2, or we can set here beta we are added here. So tan of alpha 2 is equal to Vf2 upon Vw2. So that comes out to be 16.7768 degrees. Okay. Now determination of number of backward chord wheels. So how many number of backward chord wheels are required? Okay. Now this formula I have taken it from the standard book as a centrifugal pumps and blowers by the Austin Church. Okay. So this formula Z is equal to 6.5 into the bracket d2 plus d1 upon d2 minus d1 into sine of theta 2 minus theta 1 upon 2. So d2 is equal to 280 mm, d1 140 mm, theta 2 12.35 degrees and theta 1 is equal to 7.3078 degrees. So z comes out to be, by putting all these values, z comes out to be 2.3186, but still we have to consider minimum number of blades as 4 or 6. So now I have here consider z is equal to 6 for our calculations. Now the radius of curvature of the backward chord veins. So whatever the backward chord veins are there, I have to find out the radius of curvature, and this is standard formula, you can get it from the Modi set. Okay, so R is equal to R2 squared minus R1 squared upon 2 times R2 cos of beta 2 minus R1 into cos of beta 1. R2 140 mm, R1 70 mm, theta 1 7.3078 degrees and theta 2 as 12.35 degrees. Okay, if you put all these values, I will get the value of radius of curvature as 109.16 mm. The next one, width of the blade at the exit and the inlet. This is the width of the blade at the exit, at the inlet, sorry, and this is the width of the blade at the exit. Okay, so now standard formula Q is equal to pi dB into K into Vf, where Q is equal to same 0.02778 meter cube per second, D2 is equal to 240 mm, D1 is equal to 140 mm, Vf1 is equal to V1, that is equal to 2.7072 meters per second, Vf2 5.3561 meters per second, value of K is equal to 0.9 for the from the standard book for the centrifugal pump. Okay, so from this we will get the value of B1 is equal to, that is nothing but the velocity of the impeller blade at the inlet. B1 is equal to 21.25 mm. Then the B2, that is the velocity of the blade at the exit, that is the thickness of the blade at the exit, that comes out to be 0.0537 meters, that is nothing but 5.37 mm. So by this way we can calculate the width of the blade at the exit, at the inlet and at the exit. Similarly, for the thickness of the blade, this is a standard formula available over here. So now just put all the values, already we are calculating it, and from this I will get the value of T1 is equal to 2 mm. Okay, and T1 is equal to 2 mm and T2 is equal to 3.1271 mm. So by this way we can calculate the value of thickness. Now we have to go for shaft design of the impeller. Now initially this is the total entire shaft. So first of all we will see how many components will be fitted on the shaft. Okay, so let it be, this is the first L1. So this is the total length provided for the locking, or we can say that the lock nut of the impeller, so that impeller will not be moved outside. Then L2, this is the total L2 is nothing but the impeller, this is the length of the impeller which will be fitted on the shaft, length of the impeller which will be fitted on the shaft. Then L3, this is the total length provided for the stuffing box. Okay, so entire stuffing box is fitted over this length L3. Now length L4 plus L5 is plus L6 is nothing but the total length provided for the bearing housing. Out of that, L4 is for the bearing set at the initial conditions, and L6 is nothing but the length of the length provided for the bearing at the last. Okay, generally we have to assume, it means that while selecting the bearing we have to assume that the entire radial load is shared by the set of first. It means that this bearing won't carry any axial load, so this bearing can carry only radial load, and the bearing at the exit carry the entire axial load. Okay, and very small amount of radial load. And last one, this is the last part, L7, this is for the space for the coupling, where coupling is to be fitted. Okay, now now this is entire we can say that the loading arrangement for the shaft. Now it's not very easy to decide the dimensions of the shaft. Okay, because it has to carry the radial load, it has to carry the tangential load, it has to carry the axial pressure, and all the things it has to carry. So what we have to do, it for simplicity, we are going to calculate the value of shaft diameter based upon the torque acting on it, and we have to consider 30%, 30 to 40% greater for the bending purpose. Okay, so P is equal to 2 pi nmt divided by 60, power P 25 kilowatts and 2880 rpm. From this we'll get the value of torque as 82893.19 Newton mm. Okay, so now I have assumed the shaft material as C40. So from PSG 1.9 we'll get the sigma y 330 Newton per mm square. Factor of safety is equal to 3. Sigma T design is equal to 110 Newton per mm square. Tau design is equal to 55 Newton per mm square. And from this we'll get the shaft diameter as 19.72 mm. Now considering the bending failure, we have to consider somewhat higher. Okay, so 30% greater. So answer is comes out to be 25.64. Now for simplicity, I have considered still somewhat more value as 30 mm. So the impeller hub diameter dh is equal to 1.5 into d2, that is nothing but 45 mm. Now assumption is into the length of the shaft. Already I have explained it in the previous slide. Now L2 is the length of the impeller section. Okay. Now L2 is equal to how much? B1 plus thickness of cover plate. Already we have seen it. Suppose this is the impeller, then this is the open impeller. Then we have to provide the shroud plate as well as we have to provide the cover plate. So thickness of both these plates we have to consider. Okay. So here L2, that is B1, maximum width of the impeller is the B1 21.25 mm plus 5 mm, that is thickness of the shackle plate, sorry, thickness of the uh, cover plate plus thickness of the base plate plus some clearance we have to provide it, so plus 5, so that is 36.25 mm. Now how to assume this length? It means that we have made the assumptions for L2. Now how to make the assumptions for remaining length? Now for that reason, just try to refer Kirloskar pump division manuals, because in any of the standard book you won't find such kind of assumptions or such kind of suggestions over there. So as per the KPD manuals, I have assumed that L3 plus L4 plus L5 plus L6 means this is L3 plus L4 plus L5 plus L6 should be greater than 5 times of L2. So 5 times of L2, this comes out to be 181.85, but still I have considered somewhat high value, that is 185 mm. Okay, now already we have assumed the value of diameter D2 is equal to D7. Diameter D2 is equal to D7, okay, is equal to 30 mm. Okay, now D3 means that this is the total region provided for the stuffing box. So consider 2.5 mm strip on both sides, so on the radial side. So I will get the value of D3 is equal to 35 mm. So again this is a step over here, again one more step for the uh, not to fit the bearing. So I have considered D4 is equal to 40 mm. Okay, again D5, this is spacing between the two bearing, I have considered again 45 mm, and again a 5 mm step of 40 mm, and finally D7 is equal to 30 mm. So this is about the assumptions. Now determination of weight of the impeller. Now in order to calculate the radial load and the axial load, I have to calculate the weight of the impeller. So now what is the weight of the impeller? So tentatively, the weight of the impeller nothing but the weight of the vanes, that is backward chord vanes, plus weight of the crown plate, plus weight of the base plate, plus weight of the hub. Now W. Now here instead of this curve in this backward chord vanes having the curvature like this, so instead of curvature we have to assume the blade area like this for simplicity. Otherwise, it will be very difficult to calculate and uh, approximate the things. Okay, so now weight of the impeller W is equal to this rho into the bracket, it will be number of blades Z into 1 half into bracket B1 plus B2, that is nothing but the summation of parallel sides, okay, into the distance between the two parallel sides, nothing but the R2 minus of R1 into thickness T, okay, plus pi into R2 squared, the second one, that is the weight of the crown plate, pi into R2 squared into thickness of plate, that is the entire plate, plus. But now for the crown plate, there should be the hole, म्हणजे एका साइडला आपल्याला इथे होल ठेवावा लागेल for the entry of the water. So that's why the volume of that plate is equal to pi into R2 squared minus of R1 squared into thickness of the plate, plus pi by 4 into dx squared minus ds squared into A2, is nothing but the volume of the hub, and whole volume multiplied with density, you will get the weight of the impeller. And density for a cast iron is above given at 0.072 Newton per centimeter cube from PSG 1.1. Now if you put all these values, so finally you will get the answer as W is equal to 43.61579 newtons. It's a rough idea, it's not exact idea, I know it, but in order to go for the force analysis, I have to go for this assumption. So W, that is nothing but the weight of the impeller, it comes out to be 43.61579 newtons. Now dynamic and a radial load acting on the shaft. Dynamic radial, first of all we think about the radial load. Okay, so dynamic radial load acting on the shaft is equal to m omega square into E. So as per the standard pump manuals, we have to assume certain eccentricity, and that due to that eccentricity, whatever the load acting, and that is assumed as a radial load. So here I have to calculate the value of mass of the impeller. So W upon 9.81, that comes out to be 4.4460 kg. Now omega is equal to 2 pi n by 60, that comes out to be 301.5928 radians per second. Now I have assumed the value of eccentricity is equal to 5 mm, that is equal to 0.0005 meters. Okay, so if you put all things over here, so I will get the finally radial load is equal to 2022.0011 newtons. Now axial load. How to calculate the value of axial load? So axial force due to the pressure between the suction and the delivery side, that is the pressure difference between the suction and delivery side. This is nothing but the cause of axial force, as well as the axial force due to the change in the direction of flow. So radially, axially entry and radially exit of the velocity of the liquid. Okay, so due to this change in direction, again axial force is created, and this is a standard formula, that is a axial force is equal to hs into rho w into pi by 4 into d1 squared plus hd into pw into pi by 4 d2 squared minus of d1 squared plus rho w into q into vs. So now if you put all these things, already we have all calculated it in the previous slides. If you put all the things, you will get a total axial force as 2291.9165 newtons. Now bearing selection. Now in order to calculate the bearing, we have to first of all locate the bearing. So at the center, now this is the location of first bearing, and this is the location of second bearing. Now as initially I have discussed, the bearing set 1 carries only radial load, and the bearing set 2 carries the entire axial load and with small amount of radial load. So first of all I have to make an assumption for the length between the centers of the two bearing. ह्या दोन centers bearingच्या centerच्या मधलं जे distance आहे, so for that reason we have to make the assumptions. Okay, so we have made the assumption that the distance between the two bearing center is equal to total L divided by 3. Now the total L is comes out to be 203.5 mm. With reference to the guidelines from the pump manuals, the bearing center one should carry the large amount of carry the radial load only, and the bearing set 2 carries the entire axial load and a very small amount of radial load. Now already we are calculating the value of total L over there. Okay, now total L is total L divided by 3, so that comes out to be how much? 61.66 mm. Already answer is 185, 181 point something, we have assumed it to be 185, so 185 divided by 3, that is 61.66 mm. Okay, plus this remaining, plus how much, this total is how much? This total is how much? L3 plus this total nothing but the L2 plus L3 plus L4 plus L5 plus L6 plus L7. Just a minute. So now from this total length is comes out to be 203.5 mm, and out of this the distance between the location of the bearing, location of the center of the hub, center of the impeller section, and this bearing center comes out to be 141.84 mm, and the remaining is 61.66 mm over here. Okay, so this is the total assumptions we have made it, and by applying the equilibrium and by applying the moment, we are getting it value of FBR1, that is nothing but the radial load at the first bearing is how much? 6673.32 newtons, and the radial load at the bearing number 2 is equal to 455132 newtons, and the entire axial load is nothing but the FBA2. Okay, now selection for the bearing 1. So diameter ds is equal to 40 mm, already we have assumed. Okay, now RPM N2880, assuming the life of the bearing required is 5000 hours with respect to PHG recommendations. Now L90 is equal to LH90 into 60 into RPM, and that comes out to be 864 millions of revolutions. Now this is a standard formula, P effective is equal to CR into X into FR plus Y into K and whole multiplied by service factor. Now CR is nothing but the ring rotation factor. Since only outer is rotates, so CR is assumed to be 1. Sorry, only inner is rotates, so CR is equal to 1. So and FR is equal to FBR1, that is 6673.32 newtons. There will not be an axial load, so I can assume the value of x is equal to 1 and y is equal to 0, and service factor is equal to 1.2. So effective load is comes out to be 8007.98 newtons. Now from the formula of dynamic load carrying capacity, C is equal to L90 upon L10 raised to the power upon 1 upon K into P effective. Now for considering the ball bearing, we have to consider K is equal to 3. So finally dynamic load carrying capacity comes out to be 7627.1 kgf. Okay, now if you consider the deep groove ball bearing series, first three series, first for the first 60 series, 62 series, 63 series, for a 40 shaft diameter, the available capacity is less than this value. So final option is escape 6408 with the shaft diameter of 40 the capacity of the bearing is 4300. So now what we have to meditate, instead of putting a single bearing, we have to put a set of two bearing of the type escape 6408, so that the overall capacity may be greater than the required value. म्हणजे आपली capacity किती है, required capacity किती है, तो 7627, and we have the capacity of 5000 kg. So we have to provide a set of two bearing of escape 6408 whose dynamic load carrying capacity available is 5000 kg. Okay, this is all about the bearing selection for set number 1. Now bearing selection for set number 2. DS is equal to 40 same similar assumption, RPM similar assumption for the life required. Okay, only the change is here FR is equal to FBR2, which is nothing but the 4551.32, and there is a entire axial load of 2291.9165 newtons. Now if you calculate the value of FA by FR, that comes out to be 0.5035. Now for this FA by C0, it means that we have to make the assumptions regarding the E such that the value of FA by FR greater than the value of E. Okay, so for simplicity, I have assumed the value of E is equal to 0.27, 0.37, and corresponding values are x is equal to 0.56 and y is equal to 1.2. Service factor 1.2. So the effective load is comes out to be 6358.8468 newtons. Now from this we are going for the calculation of dynamic load carrying capacity, that comes out to be 6056.424 kg. Now if you refer the, now this bearing has to carry the radial load as well as the axial load, hence we have to go for the instead of plain deep groove ball bearing, we have to go for standard, instead of deep groove ball bearing we have to go for the we have to go for a selection of the angular contact ball bearing, and with reference to the PHG we have to select the, no, here requirement is too much higher. Okay, and available standard bearing, angular contact ball bearing for a 40 shaft diameter, its capacity is only 3550 kgf. Now again, instead of single bearing we have to provide a set of two bearing of bearing number SKF 73008B. Okay, for 40 shaft diameter. Now last one is the design of volute casing. Okay, now first of all we will go for the some amount of assumption. Now see, these are a different cross section. It means that the cross sectional area of the volute casing will be increasing, okay, along the periphery of the impeller as shown over here. Now this point where the variation starts, it has a point that is called the tongue of the radius, and the, okay, and the radius associated from the center of the impeller up to that point, that is called the tongue radius. And as per the standard books we have to consider it will be 1.0 times R2, so 1.05 into R2, that comes out to be 147 mm. Okay, now the radial distance between the periphery point of the impeller and the tongue point is called as a S1, that is one port thickness. So S1 is equal to RT minus of R2, that is equal to 7 mm, and S0 is the outer diameter of the volute casing. The volute casing is the outer diameter that is called as a volute, that is called as a S0. Okay, so S0 is equal to 0.9 times the diameter of the delivery pipe, that is a standard assumption from the standard references. So 0.9 into 101.6, that comes out to be 91.44 mm. Now we have to find out that angle alpha. It means that suppose this is a R2 and this is the value of tongue radius. So all two values, two should be in a one line. Then we have to find out this angle psi. Okay, so that is equal to, this is the value of RT tongue radius, this is the value of R2, that is the outer radius of the impeller, and this is the value of HI, that we have to find it out. Okay, so first of all, from this the value of RT is equal to 147 mm and R2 is equal to 140. We will get the psi is equal to 117.57 degrees, and the associated value of HI is equal to, from this geometry we can get it as a 44.82 mm. Now this is a standard formula given again in standard book RI. It means that it is the radius of the centers of this all cross sections. म्हणजे हे जे क्रॉस सेक्शन जे आपण दाखवलेत ना, या सगळ्याच्या सेंटर मधून मी एक जर कर्व पास केला, त्याची रेडियस कितीने व्हॅरी होईल, दॅट इज कॉल्ड एज आर आय. अँड radius of the variation in the radius of the impeller, sorry, not impeller, it's a KC, that is the value of RO. Okay, so this is a standard formula. So divide d2 by 2. Now what we have to do it, आता इथे आपल्याला जो अँगल पुट करायचा आहे तो अँगल सुरुवातीला 0 घ्यायचा आहे. इट मीन्स दॅट आय हॅव टू कन्सिडर धिस ॲज अ डॅटम, आय हॅव टू कन्सिडर धिस ॲज अ डेटम. म्हणजे हा डेटम पॉईंट घेतला तर इथून याच्या पुढे तुम्हाला अँगल मेजर करायचं आहे. सो दॅट्स वाय हिअर हा जो इकडचा अँगल जो आपण साय घेतला तो प्रत्येक वेळेला मायनस करत जावं लागेल. सो हिअर नॉट डायरेक्टली 90 डिग्रीज, इट विल बी 90 मायनस दिस फाय, so that comes out to be 72.43, then 162.43 at this point, then at this point it will be 252.43, and at this point it will be 342.43. Okay, now if you put all over here, I will get the value of Ri and variation of the Ri and Ro. So this is nothing but the design of volute casing. From this I will get the maximum diameter of the volute casing. Okay, maximum radius. Now design of volute casing, remaining part is a thickness. How to find out the thickness of the volute casing? So for that reason the standard formula of the strength of materials we are going to use it. For that reason the testing pressure. So we have to consider testing pressure generally 2 times the pressure generated by the pump. That we have to assume that is equal to 2 times rho g into hm. So that comes out to be 1.2753 Newton per mm square. So now selecting the material for the volute casing as GCI 25, and accordingly these are the assumptions made for the properties. So that we will get the sigma T is equal to 50 Newton per mm square. Now applying the strength of material formulas, sigma T is equal to P max into D upon T. Now D, you have to consider here 2 times RO max, and that comes out to be 2 into 238.44, that is equal to 476.88 mm. So if you put all these things over here, we will get the thickness T is 5.999, but still I have considered somewhat higher value as a 8 mm. Now how many number of beds and what should be the bed, what should be the thickness of, type of the bed, we to select it. Now selecting the material for the bed at C30, that is sigma y is equal to 300 Newton per mm squared. So all these things we are getting it from PSG 1.9. Now total load acting on the bolt, म्हणजे ह्या बोल्टवर किती ॲक्सियल लोड ॲक्ट होईल, दॅट टू ॲज्युम इट. सो FB is equal to P test, testing pressure into this entire area. So now instead of entire area, I have to consider the area at the outside of the impeller, that is nothing but the pi by 4 into d2 squared. So from this I will get the amount of force acting on the bed, okay, on the all of the bed is equal to 7856.8729 newtons. Now here I have assumed, as shown in the diagram, I have assumed 8 number of bolts. You can go for a 6 bolt also, you can go for a 12 bolts also. So here I have assumed 8 number of bolts. So divide by 8. So load on each bolt I have get it as a 9815.25 newtons. So the tensile stress acting on the each bolt sigma T is equal to 100 Newton per mm square. That is equal to total axial force upon the cross sectional area of the each bolt. From this I will get the value of D is equal to 11.1794 mm. So as per standards of PHG references, we are going for selecting a standard bolt of M14 with pitch is equal to 2 mm. Okay, so this is all about the bolt design, and this complete the entire process of the design of centrifugal pump. Thank you.